Hey there, fellow philosophy enthusiasts. Given your deep interest in how we know what we know, I thought it would be fascinating to really dive into the scientific method, but not the simplified version we all got in
Well,
school.
yeah.
We're going deep with the Stanford Encyclopedia Philosophy's take on it. And spoiler alert, it's less of a rigid recipe and more of an ongoing, evolving conversation.
Definitely. And for anyone grappling with epistemology, this is a big one, right? How does science give us this incredible understanding of the world, and what does that tell us about knowledge itself?
Exactly. So we'll start way back with those classical thinkers, see how their ideas shaped the whole thing. Then we'll hit the scientific revolution, jump into some intense 19th century debates, explore the 20th century's obsession with logic and testing,
Yeah.
and finally, land in the present, where statistics, computer models, and a focus on the nitty-gritty of scientific practice are shaking things up.
It's a wild ride through history and philosophy for sure.
Oh, absolutely. But our mission for you, dear listener, is to unpack those philosophical foundations, those juicy disagreements, and see what it all means for how we know anything at all.
And it's worth remembering, as Loudon pointed out, that while thinking about scientific method is tied up with broader epistemology, it's got its own unique path.
Right, it's asking questions specific to understanding the natural world. Okay, let's go back to ancient Greece. Plato, he was all about those abstract forms, those perfect concepts that exist beyond the physical world. You reach them through pure reason, deduction, that kind of thing.
Yeah, the senses, the physical world, almost a distraction for him.
Right. Total opposite of Aristotle. Aristotle's all about grounding his inquiry in the natural world. Observation, even though it wasn't the controlled experiments we think of today, was still key. He wanted to build a system of knowledge, what he called episteme. Not just random facts, but organized, connected understanding.
He laid the groundwork for our ideas of deduction and induction. Deduction, going from general principles to specific conclusions, and induction, working from specific observations to general ideas.
Huge for philosophy. And all this was laid out in his organon, right? His writings on logic and reasoning, giving us those frameworks for organizing knowledge, drawing conclusions.
Absolutely. And that Aristotelian model, the interplay of observation and logic, it stuck around for centuries. The medieval period, it gets kind of overlooked sometimes, but there were major refinements going on.
Oh yeah, those medieval thinkers, they don't always get enough credit.
Right. People like Albertus Magnus, Thomas Aquinas, Roger Bacon, not the Francis Bacon, just to be clear.
Right. Important distinction.
They were all wrestling with how we justify knowledge from experience, refining those processes of observation and induction.
And then bam, the scientific revolution hits. Everything changes. Math, mechanical explanations. It's a whole new ballgame.
Right. And Francis Bacon, now this is the famous Bacon, he really takes aim at Aristotle in his Novum Organum.
Okay, what's his beef?
He thought Aristotle rushed to generalizations without enough solid observation. Bacon's all about a systematic, methodical approach. Collect those observations carefully and watch out for the idols, those biases and errors in our thinking that can mess things up.
Yeah, like those mental traps that lead us astray.
Exactly. But even Bacon's super organized approach had its limitations. It wasn't quite realistic, was it? Later thinkers like Wellwell pointed out that he kind of missed the importance of creative thinking, those theoretical leaps that drive real scientific discoveries.
So you need both. Systematic observation, A&D, that creative spark.
Exactly. And then comes Newton. And man, his impact is massive. His work like Principia Mathematica and optics, it's a whole new model for doing science.
So what was so groundbreaking about Newton's approach?
Well, for us, it's the shift in emphasis. Take his law of universal gravitation. He didn't start with some abstract principle. He worked from the actual phenomena, from planets moving, apples falling.
So from observation to explanation?
Right. And his famous hypotheses non fingo, I frame no hypotheses, it captures that inductivist spirit. Build your explanations from the evidence, not from preconceived notions.
And that idea really takes off during the Enlightenment, doesn't it? The scientist is a humble observer, just letting the data guide them.
Yeah. Thinkers like Voltaire and Émilie du Châtelet, they popularized that image. But even then, not everyone was on board with this pure inductivism.
Oh yeah, there were some pretty major critiques.
Berkeley questioned Newton's mathematics and that focus on the senses. And then there's Hume, who really throws a wrench in the gears with his problem of induction.
Oh yeah, the classic problem of induction. Always a mind bender.
How can we be sure, he asks, that patterns we've seen in the past will keep happening in the future? Just because the sun has risen every day so far, how do we know it will rise tomorrow?
Right. It throws the whole idea of learning from experience into question.
Exactly. And this sparked a huge philosophical debate. It even led Kant to try to find a new foundation for empirical knowledge.
So Hume really stirred things up.
He did. And then we get to the 19th century and this famous showdown between Mill and Whewell, often framed as inductivism versus hypothetico-deductivism, but our source suggests it was even more nuanced than that.
Okay, unpack that for us.
So Whewell introduced this idea of a fundamental antithesis. Knowledge comes from both objective experience and the active contribution of our minds, what he called fundamental ideas.
So it's not just passive observation.
Right. Our minds are actively shaping how we understand the world. And these fundamental ideas, they're not universal like Kant's categories. They can even be specific to different scientific fields.
So the way we think about physics might be fundamentally different from how we think about biology.
Exactly. And Whewell emphasized discoverer's induction. It's that creative act where you connect the dots, you come up with a theory to explain seemingly unrelated observations. He called this colligation of facts.
So it's like finding the hidden pattern, the unifying idea.
Yeah, and then you test that theory rigorously. That's consilience of inductions, seeing if it explains even more, different kinds of facts.
Gotcha. So it's not just about coming up with the idea, it's about testing it in different ways.
Exactly. Now, Mill, he had a more, narrower view of induction. For him, it was the core of science, finding those regularities, those patterns that lead to laws of nature. And he gave us his famous Mill's methods for figuring out cause and effect.
Right, like isolating variables, figuring out what truly causes what.
Yeah. Both Mill and Whewell, they were ultimately concerned with induction, with generalizing from experience, but they differed in how they saw the nature of that knowledge.
So Mill's more focused on the patterns themselves, while Whewell emphasizes the active, creative role of the mind in building theories.
Exactly. And it's interesting that Mill and those who came after him, they kind of downplayed the importance of that discovery phase, that creative process that Whewell was so keen on.
So the aha moment gets overlooked.
Right. Then we hit the 20th century, and woo, things get shaken up again. Quantum mechanics, relativity, they show us that even our most cherished scientific beliefs can be wrong.
Yeah, those were paradigm shifts for sure.
It led to this focus on testing and confirmation, and this really clear distinction between the context of discovery and the context of justification. Where does the idea come from, and how do you test it?
Okay, so the context of discovery is like the brainstorming, the inspiration, and the context of justification is all about the evidence, the rigorous testing.
Precisely. And for much of the 20th century, philosophers of science were obsessed with justification. Like, how do we logically prove something is true? Or at least, how do we show it's well supported?
Makes sense, especially after all the upheaval in physics.
Right. And so we get these attempts at rigorously analyzing scientific theories. Logical constructionism, championed by Carnap, wanted to reduce everything to basic observations, build it up like a logical system. And then there was Bridgman with operationalism, saying every concept should be defined by how you measure it.
So, super precise definitions tied to concrete measurements.
Exactly. But these approaches, they ran into problems. Hempel pointed out that if you're too strict about verifiability, universal laws become meaningless. You can never observe everything. Plus, it all felt very detached from how science actually happens.
Right, science is messier than a perfect logical system.
For sure. And pure inductivism, it started to crumble too. We realized observation isn't neutral. Our theories, our assumptions, they influence what we see. And Hume's problem of induction, still lurking in the background. Plus, paradoxes of confirmation, those weird logical twists that show how tricky it is to prove something with evidence.
Yeah, confirming evidence doesn't equal absolute proof.
Right. Out of this mess comes the hypothetico-deductive method, or HD method. It's a different way of thinking about confirmation. Basically, if your hypothesis predicts something that turns out to be true, that gives it support.
So it's about testing predictions.
Yes. And Hempel's analysis of Semmelweis's work on childbed fever is a classic example. But the key here is that confirmation doesn't mean absolute truth. It's about degrees of support, how strong the evidence is, how surprising the prediction was.
So you're building confidence in a theory, not proving it beyond all doubt.
Exactly. And then comes Popper with his big idea, falsificationism. He agrees on deductive testing, but he says the key isn't confirming a theory, but trying to disprove it.
Interesting. So it's about trying to find evidence that contradicts the theory.
Yeah. There's a logical asymmetry, he says. You can never be 100% sure a theory is true, no matter how much confirming evidence you find. But one solid counterexample, in principle, can prove it wrong.
Ah, so it's easier to disprove something than to prove it, absolutely.
Right. And for Popper, this is how you tell real science from pseudoscience. A scientific theory makes risky predictions that could be falsified. He also talks about corroboration, how well a theory has survived attempts to disprove it, but he's clear that it's not about the probability of it being true.
So a theory that survived a lot of tests is more trustworthy, but still not guaranteed to be true.
Right. And Popper really disliked those ad hoc modifications, those tweaks to a theory just to protect it from being disproven.
So like adding an exception every time the theory fails?
Yeah, that's not real science for Popper. But he later admitted that sometimes what seems ad hoc can lead to genuine progress, like when they predicted Neptune's existence to explain weirdness in Uranus's orbit.
Okay, so sometimes you need to be flexible, but you have to be careful about it.
Exactly. But then the 1960s roll around, and those comfy ideas about a single, unified scientific method, they get challenged big time.
Uh-oh, what happened?
Well, Thomas Kuhn publishes The Structure of Scientific Revolutions, and he's looking at science historically, sociologically. He says science doesn't move in a straight line. It goes through these cycles of normal science within a dominant paradigm, and then these big revolutionary shifts to new paradigms.
So it's not just about steadily accumulating knowledge?
Nope. There are these ruptures, these fundamental changes in how we understand the world. And he talks about the disciplinary matrix, the shared assumptions, values, and problem-solving approaches within a scientific community. He even suggests that methods themselves might be relative to these paradigms.
Whoa, so what counts as good science might depend on the prevailing paradigm.
Exactly. And this raises big questions about the objectivity of science. Is it all relative?
Big questions indeed.
And then Paul Feyerabend jumps into the fray with his book, Against Method, and he's basically saying, anything goes when it comes to scientific method.
No rules at all.
He looked at those classic stories of scientific triumph and said, hey, if you look closely, they didn't always follow those rigid rules. In fact, sometimes breaking the rules led to breakthroughs. He even worried that science, with its authority in society, could stifle creativity and freedom of thought.
So he's saying too much rigidity can be a bad thing.
Yeah. And then we get the sociology of science, specifically the Strong program. They had this idea called the symmetry thesis. Basically, when we explain why a scientific belief is accepted, it shouldn't matter whether we think it's true or false. We should use the same kinds of explanations.
Interesting. So social factors, power dynamics, all that stuff, it plays a role regardless of whether the belief turns out to be right or wrong.
Exactly. And this really challenged the idea of a pure, objective scientific method. Thinkers like Latour, Woolgard, or Cetina, Pickering, Chapin, and Schaeffer, they all did these detailed case studies showing how social factors shape scientific knowledge.
So the image of the scientist as a lone genius, totally objective, it starts to fall apart.
Right. And then more recently, we have the replication crisis.
Oh yeah, a big wake-up call for science.
It's been tough to reproduce the results of many studies, and that raises questions about the reliability of our methods, the robustness of our findings. By the end of the 20th century, the search for that single, universal scientific method, it had kind of lost its steam in philosophy of science.
So the quest for the holy grail of scientific method fizzled out.
Yeah. But that doesn't mean we've stopped thinking about method. It's just become more nuanced, more focused on actual scientific practice. For example, statistics. It's become central to how we understand evidence, how we test hypotheses.
Oh yeah, statistics are everywhere in science these days.
From the 19th century onwards, statistical methods have become essential for analyzing inductive reasoning. They've shaped how we design and analyze experiments.
So statistics are like the tools for making sense of all that data.
Exactly. And there's this fascinating debate within statistics about hypothesis testing. Is the goal to find the truth, like Fisher argued? Or is it more about making good decisions, even when we're uncertain, like Neyman and Pearson emphasized?
Okay, so is it about finding the right answer or about making the best choice given the information we have?
Right. And this mirrors a bigger philosophical debate about values in science. Should science be totally neutral? Or do values, ethics, inevitably play a role?
It's hard to imagine doing science without some values guiding your choices.
And then we have Bayesianism and frequentism, two big frameworks for understanding evidence. Bayesianism, it's all about degrees of belief, how our confidence changes as we get new evidence. It uses Bayes' theorem to update our beliefs.
Okay, so it's like constantly adjusting your confidence based on new data.
Right. Frequentism, on the other hand, sees probability as long-run frequencies of events. It's all about controlling errors in our statistical methods.
So more about long-term patterns and minimizing mistakes.
Exactly. Both are powerful tools, but they come from different philosophical starting points, and there's still debate about which is better or more appropriate in different situations.
So it's not just about the math, it's about the underlying philosophy of how we interpret evidence.
Precisely. And in recent decades, there's been this turn to practice in philosophy of science. Instead of focusing on abstract theories of method, philosophers are looking at what scientists actually do.
So less armchair philosophy, more getting into the labs and seeing how the sausage is made.
Yeah. The goal is to describe, critique, and even advise on those real-world practices. And this has led to a renewed appreciation for the creativity and exploration in science. That sharp line between discovery and justification, it's getting blurry.
So it's not just about coming up with a hypothesis and then testing it. There's more going on.
Right. Philosophers are looking at things like analogy, visual thinking, thought experiments, all those ways scientists come up with new ideas. Nersession's work has been really important here.
So there's a logic to discovery, even if it's not as neat and tidy as we once thought.
Exactly. And there's more focus on heuristics, those mental shortcuts and strategies that scientists use to solve problems, especially in fields like biology, where they're building explanations for how things work.
Like those rules of thumb that guide scientific thinking.
Yeah. And then there's exploratory experimentation, experiments where the goal isn't to test a specific hypothesis, but to just explore, see what happens, find new patterns. This is big in fields like genomics and proteomics, where they have tons of data. Sometimes they find stuff they weren't even looking for.
So it challenges that idea of science being purely hypothesis-driven.
Definitely. And we can't forget about computers. They've transformed science, automation, big data analysis, models, simulations. They're everywhere.
Oh yeah, the digital revolution has hit science hard.
And it raises big questions. Are these fundamentally new ways of doing science, or just faster, more efficient versions of what we've always done? What does it mean to rely on these black box algorithms that we don't fully understand? How do we verify and validate simulations?
So making sure the simulation is doing what it's supposed to, and that it accurately reflects the real world.
Right. There's debate about whether validation can really give us deductive certainty, like some critics argue. Some even say simulations are blurring the lines between theory and experiment, maybe even creating a third way of doing science.
So are simulations like experiments or theories or something else entirely?
Big questions. And then there's machine learning, which can find patterns without needing specific hypotheses. It's fueling the debate about data-driven versus hypothesis-driven science.
Okay, lots to ponder there. But it's interesting that this whole scientific method thing, it goes way beyond academic philosophy.
Oh yeah, for sure.
It's part of how we teach science, how we talk about science in public. We often present it as this simple step-by-step process, the one true way to do science.
Right. But that often clashes with the more nuanced view you find in philosophy of science, and even among many scientists.
Yeah, most scientists will tell you there's no one-size-fits-all method.
Exactly. And the idea of a single best method or gold standard, it often pops up in debates about what counts as real science. Like, some say hypothetico-deductive is better than inductive, and these hierarchies can even affect funding decisions.
So the philosophical debate can have real-world consequences.
For sure. And even the way we write scientific papers, that MRAD format, it can create this illusion of a linear process that doesn't always reflect reality.
Yeah, it's often messier and more iterative in practice.
Exactly. And then you have cases like Dobert versus Merrill Dow Pharmaceuticals, where the Supreme Court actually used philosophy of science, ideas from Popper and Hempel, to determine what counts as reliable scientific evidence in court.
Wow, so philosophy in action.
Yeah, and even defining scientific misconduct is tricky. Early attempts to define it as deviating from community standards, they got criticized for potentially stifling new ideas, so it's a really thorny issue.
So the big takeaway for you, listener, is this. The scientific method. It's not a simple, fixed thing. It's a complex, evolving, and debated topic. We've gone from ancient attempts to balance observation and reason through those big revolutions to the sophisticated methods we had today.
And that idea of a single, clear line between science and non-science, it's really hard to maintain. Science is too diverse, too dynamic for that.
So where does that leave us as philosophers when we're trying to understand and evaluate scientific knowledge? Maybe instead of looking for one scientific method, we should focus on ideas like systematicity or those general standards of good inquiry.
Yeah, that might be a more fruitful path. After all, this is about understanding how we justify our beliefs about the world. And that's a question that'll keep philosophers busy for a long, long time.
Until our next deep dive, keep those philosophical gears turning.